Welcome to our next video for Stat 420. In this video, we're going to be introducing generalized linear modeling, or sometimes it's abbreviated GLM or GLIM, which, by the way, it's a little bit confusing. I did not name these things. There's also something called general linear modeling, which is different than generalized linear modeling. We don't talk about general linear modeling, but I just want to kind of make that distinction up front, that these are two different names. So if you're Google searching anything, make sure you're looking up generalized linear modeling for this. So just kind of a introduction here for this video, and in the next video we're going to talk a little bit more about logistic regression in particular. The reason that we have generalized linear modeling is because sometimes we work with different types of response variables that aren't necessarily continuous and unbounded, but rather variables that are bounded, and especially variables that are binary or discrete that we're trying to model. Because when we have those situations, a linear equation is not going to be a great choice for modeling that type of variable without kind of doing something extra, which we're going to be talking about. So just kind of what we see up here, when we have a continuous variable, it's unbounded. It makes sense to use some type of linear equation because a linear equation is going to predict a continuous value as our response prediction. It's going to be unbounded in either direction. So whenever we have a situation where we're trying to model a variable that is bounded into a particular range, and especially that only takes specific values, it may not make a lot of sense to use a linear equation in that context to directly model that response variable, because our equation is going to be predicting values that are not discrete, that are not going to be fitting these specific values. And especially if we have that bounding as well, our model won't make sense outside of a certain range. So that's where a generalized linear model comes in. So modeling some function of the expected value of y using a linear equation. So not just directly modeling the expected value of y, but modeling a function of the expected value of y. And now that we have some flexibility with that option, we can actually choose a function of the expected value of y that does model well with a linear equation. So we call this function the link function. And this link function is what links together our prediction of the response, so our expected value of y, to a linear equation through the use of a link function. And so typically what we're trying to do is model the probability that y is going to be equal to a specific value. So if we're working with a binary response or a discrete variable response, what we want to ultimately do is try to predict the probability that y equals some particular value, like y equals 1, given some x, some set of predictor values. And so since we can't do that directly with a linear equation, we can do that indirectly by taking a function of the expected value of y that we're going to see. So the most common example would be logistic regression. Now, technically, I should also add linear regression, or we'll also use the term OLS, ordinary least squares. That is technically an example of generalized linear modeling as well. It's just the most basic example because the link function is just the identity function of y, meaning that we don't actually have to change the form of the expected value of y. We just take itself. It is the identity function that we take of y in this model. But logistic regression would be an example where I do actually need a non-trivial link function to use a linear equation here. So logistic regression is used to model a binary response variable. And so what we do is p of x here represents kind of the probability that y equals 1 given a set of x values. So this is kind of like a function in itself, where we take some function of x to produce the expected value of y, the probability that y equals 1. And so what we do, because we can't actually sensibly model the probability that y equals 1 given x with a linear equation, which we'll see in a couple slides here why that just doesn't make sense. That should be 1. So this right here, this is not a sensible equation that we could make because probability would be a bounded variable between 0 and 1. And so our linear equation would very quickly not make a lot of sense because a linear equation is not going to stay bounded between 0 and 1 and what it produces for those estimates. I mean, it can be for a particular range, but there's going to be a range at which we reach where it's no longer predicting values between 0 and 1, and the linear equation doesn't make sense anymore. And so what we want to do instead is take some function of the expected value of y here. And so this function right here, as we're going to see in an upcoming video, is called the log odds of y. It is the log odds that y equals 1. And so this is a value that produces, this is a function that produces values that are continuous and that are unbounded and that take any value without being bounded into a particular range. And as a result, a linear equation does a really good job of modeling this particular function. So right now, this probably feels really abstract because we haven't really unpacked where this comes from. We're going to talk about that later. So this is just kind of a big overview of what is a generalized linear model. Here's an example of a generalized linear model. And here are the three conditions, the three components of a generalized linear model. Number one, there is a defined distribution for the response variable for y given x. So we have some response variable y. It has a conditional distribution at any given set of x values. So given some predictor values, there is a distribution that y could take given x. So with ordinary least squares, we talked about that as being normally distributed, that for any slice of x that I might take, if I have some response variable y at some particular slice, there is a distribution that y could take that we usually assume is normally distributed at that slice. However, in the context of logistic regression, y is always going to be a binary variable. Y can only take the values 0 and 1, where 1 is maybe a category of interest, a category that we have set to be 1. 0 would be the other category. And so y in that case is not going to be normally distributed. Instead, it's going to be what we call Bernoulli distributed, meaning that it only takes values 0 and 1 with some probability that we'll just call p. And so that probability value p can change depending on what x is. So as we're going to see, maybe we have some distribution that looks kind of like this. So if this is 0 and this is 1, and maybe we have x over here, and we notice that when x is rather low, maybe we're more likely to see 1s, and maybe less likely to see 1s over here, and maybe kind of the same story here but opposite, where maybe we're more likely to see 0s when x is high. And so in this case, the conditional distribution of y given x is Bernoulli p, where p is going to vary and depend on what the value of x is. Or maybe p is higher over here. So if this is kind of our estimate for what p is going to be, maybe p is a little bit higher over here, but maybe it's a little bit lower over here. So in that sense, the distribution of y given x, where y is a binary variable, is going to be Bernoulli p, and it's going to depend on the value of x if there's a relationship there. So that's the first component of a GLM, is that there is some defined distribution of y given x. Secondly, we can express some function of the response, and really, I think actually I should say some function of the expected value of y, just to be precise there. We can express some function of the expected value of y as a linear combination of predictors. So if it is possible to do that, then I can still use properties of linear modeling in this context. Because we know when we're working with linear modeling, if we can make that expression, then we can use maximum likelihood estimates and least squares, the least squares method to fit a model and find the most appropriate parameter estimates to fit that model. So it's kind of nice if we can do that because we can use those methods that we've talked about. And then third, there exists some link function that makes this work. There exists some link function where I can take this function of the expected value of y given x and produce a distribution that can be modeled well with the linear equation. And so what we mean by modeled well with the linear equation is that this function produces a distribution of values that is continuous and unbounded would be our goal. If we can do that, then a linear equation works really well in that situation. A linear equation doesn't really work well if we have a discrete distribution or we have a lot of bounding on what y can take. So if we can make that transition and find a link function that transforms the expected value of y to a distribution that has those properties, we can do this. In the book, you're going to see a table of examples that might be helpful. It has linear regression and logistic regression, as well as Poisson regression as another example of a GLM. And I think this is laid out really nicely, where you can kind of compare how we kind of think through these components and how it looks different depending on what the response variable might be. So with linear regression, we're typically working with a continuous variable where the distribution of y given x is going to be normally distributed. We might also have a discrete variable, in which case the distribution of y given x might be Poisson. And as we already talked about, if we have a binary variable, the distribution of y given x would be Bernoulli. The possible values that y can take is also going to vary in these different cases. So with ordinary least squares, y can take theoretically any real value. It's a continuous variable. Now, sometimes realistically, we do work with variables that have some bounding. Sometimes we work with response variables that are bounded between 0 and positive infinity. That's certainly possible. And usually we just kind of make that, use it anyway, even though, technically it isn't how it's supposed to work. And technically there's a limitation on our linear model when we do that. But ideally, our response variable is not bounded. But when we do have bounding, and specifically when the bounding makes the variable now discrete, that's going to be a real problem. It's going to make linear modeling a lot less sensible a choice to directly impose in predicting that response variable. So the link name, there is going to be a link function that can work in each of these three cases. In the case where y is a continuous variable, we can actually just use the identity link function, meaning that we don't actually have to transform y, that our linear equation is directly going to predict the expected value of y given x without any link function used. Whereas if we're working with a discrete random variable, a discrete response variable or a binary response variable, these would be our link functions of choice to make that transformation and to make a linear equation work in these cases. And then, as we'll talk about in the next, the next video, we can also kind of take the inverse of this link function to solve for the expected value of y given x directly. So we have our linear equation would equal this particular function of the expected value of y. However, usually our goal is to actually predict the expected value of y given some x values. So then we can take the inverse of this, what we call logit function, and then just plug in x into this equation to directly calculate the expected value of y given that set of predictor values. Okay, so we are going to be talking about logistic regression in this chapter. in this kind of set of videos. So before we kind of leave off, I do want to kind of talk about a specific example to help bring a little bit more context to what we're doing. Again, the next video is going to have more detail here, but just to kind of center us in something that we can think about. There's some really interesting data where the passengers of the Titanic are actually recorded, including whether or not that passenger survived, along with a lot of other just characteristics, variables about each of those people. And so maybe something we're interested in doing is creating a logistic regression model to try to predict whether somebody would survive or not based on other characteristics about them. So this data set has their name, it has their sex, it has their age, it has the fare that they paid for their ticket. In some cases, it might even have their cabin number or where they embarked. So, what if we could use some of these variables to try to predict whether they survive? Do they help give us some indication of that? So in particular, I'm going to go ahead and pick fare as a predictor variable for their survival. I'm curious if there's a relationship there. So if I plot this onto a graph, so here survival is going to be represented with 1. Not surviving is going to be represented with 0, and so we can kind of immediately see, let me move myself a little bit, where people kind of fall with respect to the fare that they paid. It's kind of hard to tell from this, but I tend to think that people who paid a little bit more seem to have a slightly higher chance of survival. But again, it's kind of hard to see with all the clustering. There's a lot of overlap that makes it difficult to parse it out. But this is kind of my intuition looking at this and just thinking about this, is the probability of survival higher if you paid a higher fare? Well, let's say that I wanted to try to predict this probability with a linear equation. I can pretty quickly see that this doesn't work super well. So what I'm trying to do here is model probability of survival directly. So this would be kind of like the expected value of y given x, or I guess I should say the expected value of y equals 1 given x, which is what we also kind of call this p of x function, which is being set in this case to a linear equation. And we can tell pretty quickly this is not a great choice because since the probabilities are bounded between 0 and 1, a linear equation is not a bounded equation, so it's just going to keep going to the point where the predictions now don't make a lot of sense. So it'd be nice if I could fit an equation that is going to be bounded between 0 and 1 by changing kind of the format of what I'm modeling here. And so instead, if I use logistic regression, it would allow me to actually fit an equation that looks more like this. And so this is an equation that will be bounded between 0 and 1. So now it's more sensibly kind of predicting these probability values. And in the next video, we're going to kind of unpack how we get to this particular function and how logistic regression works.